Hi everybody, welcome to our video on arc length. Here we're going to use integration to find the length of a curve given by a function evaluated between points A and B. So here's how we're going to do it. You're going to be super surprised here. We're going to chop up the interval A to B. Now let's say I just chopped it up at a point, well, at A and B and some point in the middle. And I sample the function at those 3 points. And now, since I'm trying to get at least an approximation of the length of the curve, I just connect these up with a straight line. So we can agree these are almost certainly not going to give you the exact length of the original curve, but they'll be a decent approximation. Look, see, it goes above and below, so yeah, this is going to be a little bit longer. Same thing over here, right? This is clearly the straightened out version of this longer curve. But okay, it's a reasonable ballpark. And all we did was chop it up at one point. What if we erase this and chopped it up at some more points? All right, what if we went, say, at A, and then maybe there, and there, and there, and there, and there, and there, and now we sample at all of these different points, and then we'll connect the dots. And you can see as we do this, yeah, we're still not getting the exact value, but you can hardly even tell the difference anymore. Okay, and that's with just, what, 7 points in there. Of course, if we want exactitudes, what do? Well, we take the limit as the number of these points is going to infinity, assuming, right, that each of these is equally spaced apart. So, what is it that I need to add up then, right? What's the integral? I mean, we know all these things just turn out to be integrals, right? Arc length equals an integral. Of course, x is going to go from A to B, but what is it that we're actually going to add up here? So let me take one of these little segments and draw it over here. So let's say we had sampled at 2 points, we'd connected the dots, and well, I don't know how long this is, but I'm going to give it a name. I'm going to call it ds. Okay. Now, if I make a little right triangle here, the distance between the input points, right? That's this distance over here. Well, we always gave that the same name, right? As you went to smaller and smaller, we called it dx. Okay. Now, of course, if I change the x, the y coordinate changes, and that's, well, what you see here. So we'll call that change dy. And now we have a little right triangle, and so using the Pythagorean theorem, we actually get a nice relationship between dx, dy, and ds. Namely, ds squared is going to equal dx squared plus dy squared. All right, now I'm going to assume here that ds is some positive number since, well, we're looking at lengths. So if I take the square root, I don't have to worry about plus or minus. So my ds equals the square root of dx squared plus dy squared. Now I play a little factoring game. I'm going to factor a dx out of both of these terms. And you might say, well, there's no dx over here. And well, okay, you're right. Okay, and actually it'll be a dx squared. So if I factor a dx squared out of the first term, I get a 1. Well, there isn't one to factor out of the second term, so I'm going to have to actually just divide by it. So I get dy squared over dx squared. Okay, now let's just do a little reality check. Let's distribute the dx squared back in. Dx squared times 1 is dx squared. Good there. Dx squared times dy squared over dx squared. Well, the dx squareds will cancel, and so I'll be left with dy squared. Hey, that's exactly what I started with, so I'm okay. Now, dy squared over dx squared, that's, wait, dy over dx, that's the derivative, right? That's your f prime, all right? So I could rewrite this as dx squared times 1 plus, I'm just going to write it as, let's say even y prime, right? F of x, that's y. Let's just call it y prime squared. Okay, now I have a square root of a product, dx squared times 1 plus y prime squared. And so ds is equal to, I can break up this square root, and let me get the first bit last and the the last bit first. This is 1 plus y prime squared, and then the square root of dx squared will be dx. So that actually tells me that my ds is root 1 plus y prime squared times dx. Now, why did I want this ds? Well, remember, what am I trying to add up? Well, I want to add up the lengths of all these little line segments, and that's exactly what the ds was. So over here, I actually could write, I'm just going to add up all the ds's. But since I'm integrating and the x is the input variable here, it's better to rewrite my ds in terms of x's, and now we have a way to do that. So I can rewrite this expression as the integral from a to b of the square root of 1 plus y prime squared dx. Okay, and if you prefer this y prime, you could write it as dy dx, or you could write it as f prime of x. Okay, any way you feel most comfortable. Okay, so that's the arc length formula, right? You just integrate the little ds's. Yeah, but the ds's, okay, that's a little more complicated expression. And, well, how do I remember this complicated expression? Frankly, I don't remember it. I remember how I get to it, okay? And it's really just the Pythagorean theorem, starting from this nice little triangle of differentials. All right, let me wipe this off. We'll do an example where we use the formula. But you're going to find this is one of the easier things we do in this course, because there is actually just a formula to use here, okay? Let's see an example, though. Okay, so in this example, we're going to try to find the arc length of this curve, which is really just supposed to be a quarter circle. All right. Now, back in elementary school, they gave you a formula for finding the circumference of a circle. If you knew its radius, and I'm telling you here the radius is 1, then you knew the circumference was 2 pi. So if you just want a quarter of it, that's 2 pi over 4, or pi over 2. So we already know the answer to this, okay? But I want to show you the power of the method. Now, we know that an equation which gives a circle with radius 1 centered at the origin is x squared plus y squared equals 1. So we're going to use this, and actually we're going to be a little clever about it, all right? Because here's the deal. If we want to use this arc length formula, we're supposed to solve for y, and we can, okay? We need to solve for y to take a derivative, right? So we solve for y, and we get y equals 1 minus x squared. Okay. Again, normally when we take a square root, we want a plus or a minus, but since we know we want the upper half, we just take the plus version. Okay, but this is kind of nasty if we have to take a derivative of it. So instead, I want to use implicit differentiation to take a derivative. So I go through and I take the derivative here. Derivative of x squared is 2x. The derivative of y squared, remember you got to use the chain rule here because y is a function of x, is 2y times y prime equals, then we need the derivative of 1, that's just going to be 0. Now I can solve for y prime, and that's pretty easy, right? I just subtract the 2x, and then I divide by the 2y. And when I do that, I get y prime equals, well, the 2's will cancel, negative x over y. Okay, that negative doesn't bother me too much because I know I need to square the y prime. So y prime squared is going to be x squared over y squared. Okay, so this is a little easier approach when you have a function given implicitly to actually taking the derivative instead of having to solve for it. And it's just, I mean, you can do it, of course. It's just a little nastier over there. Okay, so in our case, well, let's see. We want to compute the arc length, and we need to know the a and the b. Well, the arc, well, that's just coming from x goes from 0 to 1. So I integrate from x equals 0 to 1. And then I need a square root of 1 plus y prime squared, which is x squared over y squared, and then dx. All right, well, we're not like super thrilled here that we have this y squared, but that's okay, right? We can mess around a little bit. Let's see, what if I turn this into y squared over y squared? All right, so I'll take this 1, and I'll turn this 1 into y squared over y squared. Because now I have the integral from 0 to 1 root, well, let's see. I have a common denominator, that's why I did it in the first place. I have y squared plus x squared over y squared dx. And let's see, y squared plus x squared, same as x squared plus y squared. Where have I seen that before? I can't remember where I've seen that before. Right, yes, x squared plus y squared is 1. So what does this equal? This equals the integral from 0 to 1 root, okay, that numerator is just 1. And what's on the bottom? Y squared. Well, we did solve for y here already, which means we actually know what y squared is, or we could have just solved this for y squared. It's just 1 minus x squared. So 1 minus x squared dx. And I can rewrite this because that root 1, well, it's just going to be 1. So I get the integral from 0 to 1, 1 over root 1 minus x squared dx. And now we're back in our trig substitution video, right? We have the a squared minus x squared, so that's going to let us use a substitution. That substitution that we'll use is going to be x equals, well, the a is 1, so x equals sine theta. Okay, I won't go through all the detailed steps here. I'll let you do that. But after you do the substitution, our output is actually just going to be arc sine of theta. Isn't that nice? Evaluated between, let's see, or rather arc sine of x, excuse me, evaluated between x equals 0 and 1. And arc sine of 1 is exactly pi over 2. And arc sine of 0 is 0. So that actually gives us our answer of pi over 2. All right, so this mess of work here corroborates what we knew all along about the arc length of a circle. But this is going to be a lot more versatile. Like, say I didn't have y equals root 1 minus x squared, but I had y squared equals root 1 minus x squared. Well, all of a sudden, this is a completely different curve. And you didn't learn a formula for that curve when you were in elementary school, all right? Or let's say you want to know the arc length of some sort of a trig function or an exponential function. We just don't have formulas for those, but this arc length formula is going to give us a way of attacking the problem. Now, I'm going to make one word of caution here. Because we're trying to compute integrals, and because we have this square root in there, if your functions are not carefully chosen, there's a very, very good chance that the integral you have to compute is not going to have an elementary antiderivative, which means arc length problems in the real world, more often than not, you need to use the numerical integration techniques that we worked on in another video.